So let's continue with talk by Susanna de Rezende, telling us about clique.
So this is continuing a bit on the lines of Albert's talk, talking about clique and average case complexity. This is based on a recent joint work with Aaron Potekin and Kilian. So Albert gave already, I think, a great introduction to this talk, so I can skip a few things, but just okay, we're interested in the clique problem. We're given a graph G, an integer K, and we want to know whether G contains a k-clique. And we know this can be solved in time n to the k, simply exhaustive search, look at all subsets of size k, see if any of them are clique. And we're interested in understanding if this is optimal. Just a second. Okay. So there are many results in computational complexity about how hard this problem is. It's been studied, since the early ages of NP completeness, and there have been, results in particular under ETH that we actually require time n to the k, where the dependence should be linear in k and exponent. And it's been studied in these different models. In proof complexity, however, there's much less to be said about the exact lower bound for clique. So I will define exactly what this clique formula is later on, but now it's a formula stating that a graph G that's given to us has a k-clique. Okay. So what do we know in proof complexity? As Albert also mentioned, there are tree-like resolution refutations in size n to the k, because tree-like resolution can do this exhaustive search. In terms of lower bounds, well, we know for tree-like resolution, both worst case and average case matching lower bounds n to the k. And actually, to generalize this to other proof systems, even for resolution, it's an interesting problem because it really requires new ideas. It doesn't follow directly from, if you really want to get the tight lower bound, it doesn't follow from width, from random restrictions. It's the techniques we have don't give us something there. So it's an interesting problem also to develop new techniques in proof complexity. And a few years ago, we had the result for regular resolution showing average case hardness for this system. And in terms of tight lower bounds, that's pretty much all we have in proof complexity. And here the average case, I just mean it's a random graph, n vertices, and sample every edge with probability p. And I choose p so that there's no k-clique, somewhere close to the threshold. Okay, I'll talk about other clique results later on, but just in terms of tight results, this is basically what we have. And for this talk, I'll be focusing on Sherali-Adams, which Albert called Sum-of-Monomials. So here we have a set of variables where I think of two formal variables, one for xi, one for not xi. And I have the Boolean axioms. I represent clauses as polynomial equations. And I consider these Boolean axioms and the polynomial equations I get as the axioms of the proof system. And Sherali-Adams derivation that a polynomial should be non-negative, I simply multiply all my axioms by any polynomial. If there's a satisfying assignment that sets everything to 0, I'm going to get 0 here. And all my monomials are always non-negative. And I multiply them by some non-negative coefficients. So this should be non-negative. So this should be a proof that P is non-negative. So what complexity measures we're interested in here is degree, maximum degree of all the polynomials appearing in the proof, and the size, the number of monomials, if I expand everything as a sum of monomials, how many monomials I get. And refutation to show that the axioms are unsatisfiable would be to derive -1, because that would be saying that -1 is greater or equal to 0. Okay, and what we'll actually be considering here is the unary version of Sherali-Adams. So the restriction there is that the coefficients have to be plus minus 1. Okay, and then when I count the size, I'm just looking at the number of monomials. So if I did want to have a larger coefficient, I actually have to write out the monomial several times. So this is the proof system we'll be considering. It's unary Sherali-Adams. Here, there can be minus 1s. Yeah, only here.
Now a refutation should be like a minus and a possible.
It doesn't have to be because I can always like sum, if I get like minus m, I can always sum things here. So you can still get minus 1.
Also, you have to have the axioms to talk about the twin variables, right?
Yes.
And those have minus, okay, so
Yes,
where do you put those axioms?
They're all
In the
with
use of
actions.
these? Okay,
yeah, I'll go with it.
right.
Why is this complete?
Right. Well, it can, if I have a Sherali-Adams proof, we can have Sherali-Adams proofs which are with
Integers.
with integers, and then I can just write out everything.
It's Adams is complete for integers.
I think if you start with clauses, then yes. I mean, yeah. Like in particular, it can, like if you have a tree-like resolution refutation, that's very easy to see that you can actually.
But p is still minus 1 under this regime.
Yes, yes, yeah. But even without this, it's complete. And in that case, it's not minus 1. Yeah, without this, then you have to allow for like larger coefficients. Yeah, so since I'll mention no-Stolen-Satz later on, no-Stolen-Satz is just not allowing this part. And then here I have to allow, can't restrict to minus 1, but anything negative would be fine. Okay, so these are some proof systems you might have seen now during these last days. These have come up more. We have tree-like resolutions, and then the Stolen-Satz, Sherali-Adams, the Sum-of-Monomials, sum of squares up there. So what do we know? What we mentioned before, what do we know in terms of tight lower bounds for these proof systems here is only tree-like resolution. So in order to like make progress here, we can also study like intermediate proof systems. So that's what we did. We studied regular resolution. And these are these unary versions, which I'm considering this talk, which are also intermediate. And it's been shown.
What does R indicate?
Yeah, so this indicates simulation, and R indicates that it simulates over the reals. So no-Stolen-Satz you can define over any field, and Sherali-Adams simulates no-Stolen-Satz only over the reals. Yeah, so in that earlier work, we showed this hardness for regular resolution, and in this work, we're considering unary Sherali-Adams. And just to mention, like it's like it's been proven that these are incomparable, like resolution and unary Sherali-Adams. Okay, so yeah, so these results are tight and they're average case lower bounds. And here, just to mention some related results. So for resolution, we do have other results which follow from some kind of width argument, but they're not tight. They don't not really like n to the k. So I'm not mentioning them too much here. We have some for a specific encoding of clique, it's easier to prove lower bounds, and then we also have lower bounds even for res k. And there are also like degree lower bounds for sum of squares in the average case complexity, but not size. So in terms of tight size, that's all we have. So the clique formula. We're going to consider the block encoding, which is somehow the encoding that if we can prove lower bounds for this encoding, this implies lower bounds for like natural, like all the natural encodings. So it's like a stronger encoding to work with. So we consider that we have k blocks and variables per block, and should be much larger than k. So this is not really up to scale. And we have two types of clauses. We have clauses that say that for every block, there must be one member of the clique in that block. So we're looking for a k-clique with one vertex per block. And then we have these non-edge axioms. So for every pair of vertices that do not have an edge between them, I add a clause saying that they can't both be clique members. Okay. So actually, there's one more n to the k lower bound, which is for an algebraic proof system. I didn't mention it because it's actually for very restrictive, no, still in SAS. If we do not allow the use of these like negated variables, and this is like a very weak proof system, it can't even like simulate tree-like resolution, like there's exponential separations. But let me just like show how this is a really simple lower bound, and it's a nice result because it actually shows that for any graph G, the size lower bound is the number of cliques, not maximal cliques, but just any clique in the graph. So that's the number of monomials that has to appear. And the proof it's very syntactical. It's very simple. It's basically, you consider the axioms. And here I have a 1. If I'm going to syntactically derive 1, the 1 must appear on the other side. And it can only come from these axioms because there's no other 1 appearing here for other axioms. So it must come from here, which means that it must be multiplied by some 1. And now I'm getting a whole bunch of variables with degree 1. And those must cancel out somehow. So now again, I analyze how they will cancel out. And they will, okay, still have to come from here. And the idea is that the only things I can cancel out not coming from here is when I have an edge missing. And then I can cancel them out here. So I will, in such a way, be constructing all possible cliques. So it's a very like syntactical argument. And this was all that was known for any algebraic or semi-algebraic proof systems in terms of size lower bounds. Yeah.
This doesn't simulate tree-like resolution, but it's not similar. It's incomparable.
It's incomparable to tree-like resolution, yes.
But it's interesting because there is a way of the tree-like resolution lower bound for k-clique. That is a different proof. It just counts the number of maximum cliques. So the number of the leaves of the tree-like proof is the number of the maximum cliques.
Ah, okay.
So
Okay, this is not even
similar.
maximal.
Oh, okay.
This is all cliques. Yeah. Yeah, but yeah, that's okay. So how do we prove unary Sherali-Adams lower bounds? We want to define what we call a pseudo-measure, which will map polynomials to some real number. And we wanted to satisfy that axioms, they should be approximately 0. Like if this were satisfiable, then there would be an assignment that would set this to 0. I'm just saying that, okay, it has to be approximately 0, which formally means that it's going to be bounded by some minus delta delta. For other monomials, I want to say that they're approximately non-negative, which formally means that they're like larger than some like small minus delta. And then if I have these two properties, then I have a size lower bound, which is my measure on 1 divided by delta. So to see why this is the case, if we just apply this measure on both sides, the largest contribution I can get from any monomial here to getting to minus mu of 1 is minus delta. And also from here, the largest contribution, negative contribution I can get is minus delta. So I need at least mu of 1 over delta monomials to for this refutation. And I'd like just to point out that this measure, we actually have to define it for all polynomials and not only for bounded degree. Like usually when we prove Sherali-Adams lower bounds, we define a pseudo distribution for only for things of small degree. And here we really wanted, it has to hold for all polynomials. And this is standard. We define this measure on monomials and just extend it linearly to polynomials. Okay, so this was our clique formula. And now I'd like to introduce the objects which we'll be working with. These are k tuples. They're just k vertices, one from each block. And we can think of these as candidate k-cliques. So we're trying to rule out that no k tuple actually forms a k-clique. And I can view a monomial, or like if this were also a clause, I can view it as what I'm calling a rectangle, which is the set of all k tuples that are ruled out by this monomial. And what I formally mean is that if I were to set the variables in the k tuple to be my clique member, so those are set to 1, everything else is set to 0, then my monomial gets set to 1. Okay, so here's an example. If I set these vertices, any of these vertices, like 2 of these, to 1, I'm forced to set these to 0, which means that this monomial will evaluate to 1. So this is the rectangle of all the k tuples that are ruled out by this monomial. So any k tuple here will set this to 1. Here's another example. This is actually an axiom. There's no edge between x1 and x5. And anything that contains that sets x1 and x5 to 1 will set this monomial to 1. So this would be the rectangle corresponding to an axiom.
So you run over the capital VI is all possible components of which size?
Size n. The VI's have size n.
So what's the size of this total contradiction?
The number of vertices in the graph is n times k. The number of axioms is like n squared times k squared. Yeah.
All right. But you run over all size n sets, which is n to the k. Sorry, yes. N. How is it squared?
How is it?
It says each block VI.
Yes.
So if each block is of size n, and your number of vertices is, let's say, m, then you have to have something exponentially n to choose it.
Sorry, I don't understand. But what this is saying is that I want one clique member per block.
Yeah, but blocks are not fixed. It's
Yes,
all-
they're fixed. They're fixed. Sorry. Yes, they're fixed. Yeah, sorry. Okay, and then just one last example. If I consider the monomial 1, then I simply have all tuples, because all tuples set this to 1. So that's a complete space. And I can view these rectangles. They're just a k-dimensional hypercube, or it's like Cartesian product of some subsets of each block. Okay, so the pseudo measure we define, it actually satisfies much more than we require. It's actually like a progress measure on the monomials. What I mean here is that we could intuitively say, like, given a rectangle, how much progress does it represent, like towards ruling out all the k tuples? And like here I have like 2 examples, and like if I were to ask which one represents more progress, well, intuitively it's like, well, this one has to represent more progress because it's just ruling out more tuples in this one. This one's like strictly contained in that. So this one represents more progress. I'm ruling out more things. But how can, we formally define this? Well, axioms should really represent not much progress because they're given to me. So this is an axiom that shouldn't be much progress. And if I consider this the set of all tuples, well, that should be complete progress, right? I just derived one. What about for a general rectangle? What should be like the right measure of progress? So in proof complexity, sometimes we consider this, what is the minimum number of axioms needed to derive a rectangle, and consider this as a measure of progress that's useful, like for doing degree or with lower bounds. For size, the natural measure of progress is simply what is the smallest derivation of the rectangle. So we could define this as progress. But we know like automating, finding smallest iterations is not easy. So what's interesting here is that we actually have like a measure which captures precisely the statement. So let's see, yeah, what is the expected behavior of a progress measure? Well, axiom should be approximately 0. Large rectangles, the progress should be roughly the size of the rectangle, because if it's large enough, it should kind of behave randomly or like as expected. Not too many weird things can happen. What happens like if some rectangles contain some small blocks? Then it's not so clear. It could be the case that, well, these were just some axioms put together. It was really easy to derive. Or it could be the case that, no, this was actually like a clique. It was a lot of work to derive this. So when we have small blocks, it's not obvious what the measure should do. So for this, we had to define some kind of decomposition, like analyzing small blocks vertex by vertex. This is a decomposition for like any rectangle. I can just decompose it into rectangles where I want only one vertex per small block. So here I'm like decomposing, and then I can recursively decompose until in the end, either I have a large block or I have a block of size 1. And this can be done so that we actually have a partition of my original rectangle. And now I can actually analyze. I can look at these are like single small tuples. I can see whether they're a clique or they're just derivable, just an axiom. So then I can actually analyze this. So let me explain this in a little bit more detail. So we can get this family of rectangles where every rectangle is either an axiom or contained in an axiom, where I think of the measure being approximately 0. It's the other option, it's like it's a clique and on small blocks, and otherwise it contains large blocks. And then I think of this as a good rectangle, and measures of good rectangles are just approximately the size of the rectangle. Or R is just so small that it's like negligible. And then I can say the measure is negligible. And then, so I can define my measure of my original Q as simply the sum. Since this is a partition, it's simply the sum of the measure of all the rectangles that I got from this decomposition. So this is morally what I want my measure to satisfy. But it should also satisfy additivity. So here I'm ignoring these the axioms with the negated variables. And what these are really saying is that if I have like two rectangles which sum up to another rectangle, I need their mu's to be the same, like the sum of the mu's to be equal to the mu of the summed rectangle. So I need to define a measure that satisfies these properties. So I'd like to do 2 quick failed attempts, so very naive ways of trying to define this measure. So the first naive attempt is just, I'm defining the measure as being the size of the rectangle. Okay. Why doesn't this work? Yeah.
Rectangles overlap.
The rectangles overlap, but that's not per se a problem. Like it would be okay. But we wanted to satisfy like these conditions here. Yes. It's not small on axioms. Like axioms are actually like a big part of the space. The rectangles are big. So this actually fails on axioms. And then we have another option, which is, well, I mean, actually what I really care about is ruling out cliques. So I can count how many k-cliques do I have in my rectangle, and that can be my measure.
That's 0.
That's 0, right? So that fails on the whole space. Like it's just 0. There are no k-cliques in the graph. Okay, so these were like 2 not so smart attempts, but let's try to like rewrite them. And to rewrite them, I'm going to consider these Fourier characters, but what I really care is I have a graph G, I have a k tuple T, so it's just like some k vertices, and I'm concentrate just on the induced graph on those k vertices, and I have some potential edge, I evaluate my function on that potential edge. If the edge is present, then I get a 1. If it's not present, I get a -1. Okay. And then I can define this for a set of edges, and I just take the product of all edges in my set. So it's kind of like counting the parity of the missing edges. Using this Fourier basis, I can write things as the indicator that a tuple is a clique. I just sum over all the subsets of vertices that I have. If it's a clique, I always get 1 because all the edges are present. So I'm going to sum over 2 to the k choose 2, 1. So I have to divide by this. So this will be 1 if it's a clique. And if there's some edge missing, then this is going to be 0. And you can see that there's some like cancellation goes on the edge that's missing. So this is really like the indicator for a 1 clique. And if I consider like the empty set here, then the character on this empty set is simply 1, right? And multiplying an empty set. So now using these two definitions, I can rewrite these two attempts. So this one, I'm just counting the number of k-cliques. So I can just count sum over all tuples in Q of the number of k-cliques. And on this side, I'm just looking at the size of the rectangle. So I can just sum over all tuples in Q of 1. Okay. So it's like a stupid exercise, seems like it, but these two attempts. But it's interesting, one fails on axioms, one fails on the whole space. Can we get something like in between? So now for like the successful attempt. So we have our 2 failed attempts, and we want something in between. So let's choose some d, which is smaller than the largest clique in the graph. So I know there are cliques of size d in the graph. And now there's this magical step. So I do something in between these two. I don't sum all edges, only the ones that have vertex cover at most d. So by vertex cover, I just mean the number of vertices that I need that will touch all the edges in my set. Okay, I want to cover all the edges. Okay, so it's probably not clear why you would truncate at vertex cover less than or equal to d, and I don't think I'll be able to motivate this enough in the last minutes. But this actually like works. It really satisfies this progress measure. I can, given a monomial, tell you by applying this, like how hard it is to derive this monomial. Okay, so well, we can see since I'm summing over tuples, it's clearly like an additive measure. And it has the property that if I consider the expected value of anything that's not empty, since there's at least one edge present and it's here in E, and this edge is present with probability a half. I didn't say I was working on g1/2, right? So now it's important that I'm working on g1/2.
For simplicity.
For simplicity, yeah. Because of the way I defined everything, it should be g1/2. So otherwise, these have to be defined differently. So then the expected value is going to be 0 if I have at least one edge present. So we can show that in expectation, the measure satisfies everything we need. Like the whole space has measure 1, because in expectation, everything except the empty character is 0. So I'm just counting the size of the space. Also, like the same reason for rectangles, it will in expectation will have the right measure. And for axioms, it's a little bit harder to see, but it's not that hard. Since we're conditioning on some edge not being present, I can pair up these characters. They will cancel. I will only be left with things somehow in the boundary. They contain at least one edge. So in expectation, whatever I'm going to be left with will be 0. So I can show that in expectation, like everything is satisfied. So now all that's left to do is to show that this concentrates. And it seems like not so hard task, but this is where like all the work goes. And like we can observe, well, there, if we're going to do a union bound, we need to union bound over all rectangles or exponentially many rectangles. This better be like a very good concentration. Okay, how am I on time? A little bit over. Okay, so let me skip some. Okay, I'll go through this in 30 seconds. So Albert mentioned that when we prove these lower bounds, we often define random properties of random graphs that we need to prove the lower bounds. So I just wanted to say, like in this case, we have this similar two properties that were shown used before, this rich extension property that Albert talked about, and then one that we call small error sets, which is, I'd say, very similar to the clique denseness that Albert mentioned, but it's, I think, a lot more natural. It's saying is that a rectangle has all small tuples have neighborhoods of expected size, except maybe for a small set. So there might be a small set. I remove that set, then the rectangle has common neighborhoods of expected size. So we use these two more or less well-known properties, but then we need one more, which I won't have time to explain, but we need to, at least this very, very simplified version, we need sums of characters to be bounded. So I won't have time to get into this. And then, yeah, using these properties, we have to prove that random graphs with high probability satisfy these properties, and then that we can get lower bounds from these properties. Okay, so I won't go through this technical slide. So just the final remarks. So our result, it actually holds for a gap version of clique, which was not the case for a previous result for regular resolution. So here, let's say we have a clique of size at most 2 log n. Then even if I state that there's a clique of polynomial size, it's still hard for unary Sherali-Adams. And then another aspect of this proof, it's that it's essentially independent of the encoding. We could add any extension variables that depends on one block, and the proof would still go through, because we're really only working with this rectangular structure. And we get a very nice progress measure, which satisfies much more properties than we actually need. And we get an interesting decomposition of rectangles that actually allows us to capture, to see what a rectangle is ruling out. And just to mention, open problems, of course, extending this to other proof systems where I think the natural ones, resolution, Sherali-Adams, and even the students that's over finite fields. These are all open. And also getting more combinatorial descriptions of some of the properties we have, or even of the measure. I think this could be interesting to generalize this further. Okay, thank you.
A bit behind schedule, but maybe one question.
So can I imagine that in such a proof, the degree of monomial is always bounded by k?
No, the degree might be much larger. Yeah.
Okay, why? Because
there are proofs of with degree k, but here we're not ruling out. You can use larger degree.
I mean, in your graph, there is no edge in the block, isn't it?
Yeah.
There is, or there is not.
There's no edge in the block.
Then how?
But I could mention several variables in the same block.
Oh, you don't require that each vertex takes only one from them. Their multiplication is not 0.
There?
I mean, you're looking for a clique that takes one vertex per block.
Right.
So if a monomial says this block has 2 vertices, shouldn't that be 0?
It could rule out. It can say that none of half of these vertices are not part of my clique, and then it will just have to mention half of the vertices.
In a monomial.
Yeah.
You have twin variables.
Never mind.
Yeah. We can talk about it offline. Okay. Yeah, you have the twin variables. So that with twin variables, you can make huge monomial. All right. Thank you very much, Susanna. You are the speaker. I see.